So in class, we asked the question, what happens if the given probability is like this, x is greater than 80 instead of x is less than a number? How does that adjust our thinking in terms of solving the problem? So let's have a look at the setup of the problem. We've got a random variable x is distributed normally with a mean of mu and a variance of 1600. Okay, so again, remember that if the variance is 1600, that means, I'll do it in a different color, that means that sigma squared is equal to 1600, which means that sigma must be the square root of that, which is 40. Okay, I don't expect you to know that, but we can always use our calculator, of course, to work out the square root of 1600. Okay, so our usual practice then is to find the z value and then use the z value to work out what mu is using the formula. However, when we go to find the z value, menu, probability, distributions, and then inverse normal, it asks for an area, it asks for a mean, it asks for a standard deviation. What it doesn't ask for is a, if you like, a direction, like a less than or a greater than sign. So right now, we're a bit stuck. How does it know? It doesn't know is the answer to that. It always assumes the area is to the left of the value. So let's model what we've got and then do what we can do to sort that out. So at the moment, this is what we've got. We have got, oops, change color back. Normal distribution with a mean, mu, unknown, a standard deviation of 40. So mu plus 40 is one standard deviation away, mu plus 40 is another standard, etc. We know that x greater than 80 gives us an area, remember that the area under the curve is probability, of 8.84134. In other words, about 84%. That's a lot of the area, okay? So because x is greater than 80 will give us 85% of the area, it means that x, or the position here, and I'm just estimating really, would be 84% of the area. So because I've said x is greater than 80, then I'll have to look at the area above that line as being 84%. Okay, so that's what we've got. We need x less than 80. So x less than 80 is going to be this area here, like so. So we need to work out what that area is. That's not too traumatic because we know that the total area underneath this curve is 1 because it's a probability distribution function, so the total area is equal to 1. So if this area is about 84%, then this area has to be what's left over. So what's that, 16%? In other words, to put it in more fancy schmancy terms, we would say that the probability of x less than 80 is equal to 1 minus 0.84134, which is a calculator operation away. 1 minus 0.8134, 84134. That gives us 0.15866. I'm just writing it down as I go along there. Okay, so now we have an area to the left of this value here, and that's exactly what we want. Okay, I keep on saying this value as if we don't know what it is. It's 80. Okay, it also tells us, just based upon our logic here, that mu must be bigger than 80. Don't know how much bigger than 80, but it's got to be bigger than 80. Cool. So now we can find the relative position of 0.15866 on our z distribution. You don't have to write it as Z distribution, but if it helps you visually do it. So Z distribution has, or standard normal distribution, has a mean of 0. We are looking for the value of Z such that this green area here is 0.15866. So that's what we're doing, because so we flipped it around because that's what we need for the inverse normal calculator function. That's basically why we're doing it. So we find the position of the Z and then we're good to go. So we go P of Z, big Z, less than little z, equals 0.15866, means that Z is equal to inverse norm of 0.15866, 0, 1, and that's equal to, away we go to our calculator, and we can go menu, probability, distributions, inverse normal. The area is 0.15866, mean 0, standard deviation of 1, okay. That gives us negative 0.9999998. So I'll write that down, then I'll flick over the screen. You can see that's pretty close to 1, right? But at this point, I'm just going to deal in decimal places for a bit and I'll round it off at the end. So there we go. So Z is equal to 0.99998. And now we can use our formula to work out what the value of mu is. So therefore, negative 0.99998 is equal to, that's Z, is equal to x minus mu, so x is 80, minus mu, which we keep as a mu because we don't know it yet, all over sigma, and sigma we worked out before in the red is 40. Okay, so now we can calculate the solution to that. We can multiply both sides by 40, and I'm going to use the full value there, multiply by 40. That gets us negative 39.999. Now, technically, by the way, just while I'm writing this down, technically, I could use my solve function on my calculator at this point. Whether you do or not depends on whether you think it'd be easier to use your solve function or whether it's just easier just to do the calculations by hand, more or less like this. And secondly, depending on the number of marks a question might be worth. So typically, if it's worth a few marks, do a few working out steps so that they can give you part marks if you go wrong, or because they won't give you full marks just for writing an answer down. So you just need to make a bit of an executive decision as you go along. At what point am I going to use technology to do the thinking for me? It is there for you to do the thinking for you, but it's always a bit of a decision. So there we go, we've got that. And so mu, I'm going to add mu to both sides, and then I'm going to add negative 39.99992. And it does say here, find mu to the nearest integer. So at this point, I'm just going to use my brain and say, well, negative 39.9992 is roughly minus 40. And then I'm going to add it to 80. So I'm going to get mu is equal to 100. Oh, it's in blue, but we'll leave it there. Mu is equal to 120 to the nearest integer. And we're done.